In the previous set of lectures, we discussed how to handle the valuation of single cash flows. For example, you deposit $5,000 into an account today. How much will that single deposit grow to in 10 years? But what if you don't make just one single deposit? What if you make 5 or 10 or 100 of them? That's the issue we're going to begin to tackle here. First, let's review single cash flows. We can compound, which is taking a value today, the present value, and computing what it will grow to in the future. And we can also discount, which is taking a cash flow from the future and determining what it's worth today. Notice that in both of these diagrams, we're just manipulating a single cash flow. But what if we have more than one cash flow in the scenario? What if we make a deposit of $100 and then $300 and then a $200 deposit? How could we figure out what's going to be in this account at the end of 3 years? Well, we can actually solve this just like we did the single cash flow scenarios. Nothing has changed in terms of the concept of what we're doing, that is moving money through time. And to handle a situation like this, we can simply use what we already know and approach this as a series of single cash flow problems. Let's deal with the initial cash flow first, the $100 that's deposited at year 1. We need to figure out what this $100 will grow to at the end of year 3. We should remember how to do that. It's just solving for the future value. We'll make n equal to 2 since we'll be getting interest on that $100 over 2 periods from year 1 to year 2 and year 2 to year 3. The interest rate, I, is 10% per year, and we're depositing $100 in the present, meaning earlier in the timeline. We'll make the $100 negative since it's a cash outflow. We'll leave the PMT equal to 0 for now and solve for future value, and we get 121. That's what the $100 deposit will grow to. We do the same for the $300 deposit in year 2, but this time we'll change n to 1 since we'll be getting interest over just one period with this deposit. We find that the $300 deposit will grow to $330. And finally, there's the last cash flow. Since this $200 is deposited at the end of year 3, we won't be getting interest on it, so n is equal to 0. And because no interest will be earned on this deposit, the future value will remain at $200. Now pay close attention to what we've done here. We converted all these deposits all to the same time units. Before we had 100 year $1, 300 year $2, and 200 year $3. Now they're all in the terms of year $3. And since they're all in the same units, we can add them together. And we get $651. That's the present value of this series of deposits. At the end of 3 years, $651 will be in this account. Let's look at this result and see what it really means. This means that getting $651 at year 3 is equivalent to receiving $100 in year 1, then $300, then $200. If someone offered you these two options, getting the series of cash flows or the lump sum, you shouldn't carry either way because they're the exact same things, just different time units. Next, we'll add a twist to this problem that really isn't much of a twist. What if we had the same series of cash flows, but instead of seeing what will be in the account after 3 years, we want to know what's going to be in there after 5 years? The process remains exactly the same. The $100 deposit will earn interest over 4 years and grow to $146. The next cash flow will grow to $399, and the final cash flow will grow to $242. We can add those values together to get a total of $787, and that's what's going to be in the account after 5 years. Let's look at a present value scenario this time. Say there's an investment that's going to pay you $200 next year, $400 the following year, and then $600 after that. If the interest rate is 2% per year, how much should you pay for this investment? I'll draw my timeline to map out what's going on here. I need to figure out how much this series of future cash flows are worth today. That's going to tell me how much I should be willing to pay today. To do this, I'll simply find the present value of each one, then add them together. The $200 I'll receive in year 1 is worth $196 today. The $400 I get in year 2 is worth $384 today, and the $600 I receive in year 3 is worth $565 today. Since each of these cash flows is now in terms of times $0, I can simply add them together, giving me a total of $1145. This is how much the investment is worth today. And again, these values are equivalent. $1145 today is the same as receiving $200, then $400, then $600. Now let's look at some special versions of multiple cash flow scenarios. These are called annuities. Annuities are just multiple cash flows in which the amount of the cash flow is the same each time. These are different types of annuities, and there's different types of annuities, and we'll classify them by the timing of the first cash flow. We have ordinary annuities, where the first cash flow occurs one period from today. As you can see on the timeline here, the first cash flow happens at time 1. An annuity due has its first cash flow immediately, that is at time 0. Then there's the deferred annuity, in which the first cash flow is deferred until sometime later into the future, beyond time 1. And finally, there's perpetuities, whose cash flows start one period from now, but continue on forever and ever and ever. Let's do an example to get started. Let's find the present value of an ordinary annuity. In this problem here, we have a series of 3 cash flows of $4,000 each and an interest rate of 6% per year. What is the present value? On the timeline, it's going to look like this. Notice that the first cash flow occurs 1 year from today at time 1. And now we should already know how to attack this problem. All we have to do is convert the cash flow to its value at year 0 and then add them together. So let's do that. The $4,000 we get in year 1 is worth $37.73. The $4,000 we get in year 2 is worth $35.59. And the $4,000 we get in year 3 is worth $33.58. Adding them together, the value of this series of cash flows is $10,692. Because each of the cash flows in that problem were identical, each one was $4,000, we can come up with a general formula to solve for the values. Here are the formulas to find the present value and future value of an ordinary annuity. We have all the usual variables we've been seeing, but now we're adding a new one, PMT, which stands for payment. Payment stands for the annuity payments, the periodic equivalent cash flow that occurs. Applying that formula to this problem that we just worked, we see that the $4,000 is our payment. N in this case will represent the total number of payments, and I will be the periodic interest rate as usual. And you'll notice we get the same result as we did finding the value of each cash flow individually. But this is a much quicker process, especially if you have a lot of cash flows to work with. A 100 payment annuity, for example, instead of the 3 payment annuity that we just worked with here. We can do this even quicker using our technology to help us. The formulas are programmed into our calculator and into Excel, so you can simply enter the problem inputs and the computer will spit out a result for you. The inputs for the problem are given here. We're going to have 3 yearly payments, so that's our N. The interest rate is 6% per year, that's our I. We're solving for PV, and we'll set FV to 0. And the payment will be $4,000 per year. Solving for PV, we get the same $10,692 that we got previously. You might be wondering, why did we set FV equal to 0? The reason is, all of the future cash flows are already represented by the $4,000 payment that we input. There's no other cash flows to consider, so FV, the future value, is equal to 0. Later on in the semester, we're going to deal with scenarios where this won't be the case. But for right now, since all the cash flows are represented by the payment, we're going to leave FV as 0. Let's do the same problem using Excel. In Excel, we'll compute it just like a regular present value problem. We'll start with the PV function, make the interest rate 6% in decimal form. NPER will be the 3 yearly payments we have. PMT will be the $4,000 annuity payment. And we'll set FV equal to 0. For type, we'll set it equal to the default, 0, to indicate that the cash flows are occurring at the end of the periods. Close the parentheses, hit enter, and again we find the present value is $10,692. We'll do a practical example now. Say you're in the market for a car and you need to figure out what kind of car you can afford. You look over your budget and you determine you can spend $600 a month on a car payment. You contact the bank and they tell you that you qualify for a 4-year loan with an APR of 12%. With all this information, can we figure out how much we're going to be able to borrow? Well, we can draw this out on the timeline and see if this is just a regular, ordinary annuity problem. There's a regularly scheduled payment of $600 per month for 48 months. We just need to figure out what the bank will give us today, the present value. We can set N to 48 monthly payments. That's a 4-year loan with 12 payments a year. Since our time units are in terms of months, we need everything to be consistent, so the interest rate will be 12% APR divided by 12. That gives us a periodic interest rate of 1% per month. All the cash flows in the scenario are going to be captured by the payment, so we'll set FV equal to 0. And lastly, the payment will be negative $600 per month. It's negative because this is going to be a cash outflow. We're going to have to pay the bank $600 per month. Solving either in Excel or the calculator, we find the present value comes out to be $22,784. That's how much the bank will be willing to give us today. In return for getting this $22,784 today, we'll pay the bank $600 per month for 48 months. We can quickly go through an application for a future value. The process is pretty much identical. Say you deposit $6,000 a year for the next 3 years into an account paying 4% interest per year. How much will be in the account at the end of 3 years? We could just find the future value of each cash flow at year 3 individually and add them up, or we could use the formula, or we could use a calculator. N will be the 3 yearly payments. I will be 4% per year. We'll set the present value equal to 0, and we're solving for future value. The payment will be negative $6,000. Since we're depositing this, it's going to be a negative value. It's a cash outflow. Again, you might ask, why did we set present value equal to 0? We do this because all the cash flows are captured by that $6,000 payment. As you can see on this timeline, there are no other cash flows to account for, and so because of that, we'll set PV equal to 0. Solving for future value, we get $18,729. For you Excel users, here's a demonstration for you too. The process is the same as it was before, except this time we're going to use the FV function. As before, we'll let the type equal 0 for these ordinary annuities to tell Excel that these cash flows occur at the end of the period. Let's do another practical example of how we can use the N of the annuity. Imagine going on vacation and spending $2,000 on your credit card. You look at your monthly bill and see that they'll give you the option of making just the minimum monthly payment of $60 per month. How long will it take you to pay off this $2,000 vacation? You should notice that this is an annuity. Why? Because we have a fixed payment amount, $60 over a fixed interval of time, every month. Now let's set up our input table. We're solving for N, the number of monthly payments. I will be the monthly interest rate. So we take the 24% APR and break it up into 12 monthly pieces and get 2% per month. PV will be positive $2,000 since the bank is giving us $2,000 today. And FV is 0 since all the cash flows are represented by the monthly payments we'll be making. Finally, PMT, the payment, will be negative $60 since that's a cash outflow. That money is going to be coming out of our pocket. Solving for N, I get 55.5 monthly payments. It's going to take more than 4.5 years to pay this off, making just the minimum monthly payment. Let's look a little bit deeper at this. How much is this vacation actually costing us? Since we're making 55.5 payments of $60 each, we're actually going to be paying $3,330. And of that, $1,330 is going to be interest. What if instead of making just the minimum payment, you decide to pay a little bit more each month? $80 instead of $60. What impact will that small change have? It's actually going to have a pretty significant impact. The number of payments needed to pay off this vacation drops to just 35, and we'd pay about $500 less in interest. Let's finally solve for a payment, PMT. Suppose you want to buy a house which costs $300,000. Your bank offers you a 30-year mortgage with a 4.36% APR. What would your monthly payment on this mortgage be? Setting up our chart, we'll make N equal to 360 months. That's a 30-year loan with 12 payments a year. The interest rate will be, we need a monthly interest rate, so we take that 4.36% APR and divide it by 12 to get 0.363% per month as our I. The PV is going to be positive $300,000 since we're going to be receiving that money today. FV will be set to 0 because the only other cash flows will be represented by the payment that we're going to solve for. Solving for PMT, we get $1,495. That's going to be the monthly payment on this mortgage loan. Okay. So this has been the introduction to handling multiple cash flow scenarios. As you can see, there's many real-life scenarios that fit this model, so it's really useful to know how annuities work. In the next video, we're going to discuss a few other types of annuities which can be useful to know as well.